So today we're going to talk about a problem in statistical modeling, and that is when you have correlation among your predictor variables. We're going to show why it's a problem and how to detect it and some remedies for the problem. But first, let's start by setting up a scenario and going through the multivariate platform in JMP. So I've got some data here. I've got a response variable and 14 predictor variables. And the goal here is to understand the relationship between the response and the predictors. So let's start by visualizing the data in the multivariate platform under Analyze and Multivariate Methods and Multivariate. I'm going to put all the variables into the Y role and then click OK. And the output kind of looks pretty overwhelming. I'm going to close this matrix, the scatter plot matrix. I'll come back to it. The thing at the top is the correlation matrix. It is a 15 by 15 matrix because there are 15 variables, and that it contains the pairwise correlations between the variables. It's a symmetric matrix because, the correlation between x1 and y is the same as the correlation between y and x1, and that's about 0.15. So this matrix, if you have more than just a few variables, it can be fairly overwhelming. So JMP has a few ways to look at it graphically, and the first way that I like to look at it is to see it as a color map. I'm going to do color map on correlations. And these numbers now in the correlation matrix have been translated into colors in these colored squares. Red is a positive correlation and blue is a negative correlation, and these grays are near zero. You can hover over a square to get the value of the correlation. So here we can see the correlation between x11 and x2 is about 0.6, and in the table we can see x11 and x2. That correlation is there as well. Another way to visualize the correlation is to look at the pairwise scatter plots of all the variables, and JMP makes that easy for us to look at in the scatter plot matrix. Again, this is pretty overwhelming, isn't it? There's a lot of graphs here. There are some things that we can do to make it easier to see what's going on. First off, to read this scatter plot matrix, if I want to understand this graph and what does it say, who's on the y-axis? Well, you read left and right to see who's on the y-axis. So in this case, it's the y variable. And who's on the x-axis, you read up and down to see who's on the x-axis. So this graph is actually a plot of y versus x8. And again, the scatter plot matrix is symmetric. So over here somewhere, there's a graph of y versus x8 as well, except in this case, x8 is on the y-axis and y is on the x-axis. Now, because this matrix is symmetric, we don't need both sides of it. So I like to change this up a little bit. I'm going to, instead of showing two scatter plots, I'm going to go to Matrix Options and turn on Heat Map. You can play with significant circles if you want as well. And now I get that heat map of the correlations, right? That color map of the correlations, the same as we had below. Once I take a look at my pairwise scatter plots and I see that there's no kind of weird behavior, there's no skewness, there's no outliers, I will replace these points by ellipses, density ellipses. So I can turn on the density ellipses and I can turn off show points. And now the final thing I want to do is just make this smaller so I can see it. So I really like these updates that I've made to the scatter plot matrix. And I think this graph is a good summary of the pairwise behavior of the data. So notice that y is correlated with some of the x's, but many of the x's are correlated with each other, right? Both high and high negative correlations in these blues. The reds are high positive correlation, the blues are high negative correlation. And it turns out that high correlation in your predictor variables can harm your linear regression model. And this is called collinearity or multicollinearity. It's a problem in linear regression. And let's take a look at it and see what it means just on a simpler example. I'm just going to look at two predictors. So I'll minimize these windows. Back in my journal here, I've got a definition of collinearity. It happens when there's linear relationships among predictor variables and not necessarily just 2 at a time. It could be 5 variables at a time or 10 variables at a time that you may not be able to visualize those relationships with just the scatter plots of 2 variables at a time. So here's my data table, 2 correlated predictors. It's got just 3 columns in it. And I would like to fit a regression model. So I'm going to go to Analyze and Fit Model. Y is the Y, and I'll put X1 and X2 in the model by clicking the Add button. Now all day today, I want to control the output that I show you. So I'm going to be choosing Minimal Report for the emphasis, but all the reports are available from the red triangle menu as we go through. And I'm going to click Run. So you can see here we have a beautifully high R-squared value, over 99% of the variability in Y is explained by this model. I have a 1 sigma of the unexplained variability is less than 1, and this is the same units as the original data, so quite a small unexplained variability. The signal to noise ratio is amazingly high, and therefore the p-value is low. This model is useful in explaining variability in Y. My 2 parameter estimates are both, again, highly significant, and they're both positive. We probably should check the residual plot to check on assumptions of this linear model. We can do that by going to row diagnostics, and here it is. Let's plot the residual values by the predicted values. And I like to make this plot more square, and yeah, no problems here at all. Okay, so it looks like a great model, right? The residual plot looks good. I got a beautiful R-squared and significant coefficients. What's the problem? Well, here's one of the problems that you can run into with collinearity. I'm actually going to go back a step now and plot the data. So I'll go to Graph Builder. I'll pull Y over to the Y-axis and X1 to the X-axis. And here we can see a nice, strong, positive relationship, which is what I expect when I see this coefficient of 8.6. No problems. All right, let's pull X2 down onto the X-axis. And here I see a beautiful, strong relationship, but it's negative. And so why does JMP give me a positive coefficient in the parameter estimates table when the relationship between Y and X2 is obviously negative? And the answer is that these estimates down here, the interpretation of the coefficient of X2 is it's the effect of X2 given that X1 is in the model. So not just on its own, but given that X1 is in the model, when I increase X2 by 1 unit, I increase Y by 11.367 units. And similarly with the coefficient of X1, that's the coefficient of X1 when X2 is in the model. And this is the kind of thing that you can get when you have collinearity. So I'm going to actually go back to the multivariate platform and put all 3 columns in the multivariate platform. And here we can see in the scatter plot matrix, these are the 2 graphs that we just made in Graph Builder in the background here. But this is the graph that's really driving what's going on in those parameter estimates. And that is that X1 and X2 are highly correlated. They're negatively correlated. You can see it here. And when that happens, because of this correlation, X1 and X2 are fighting each other to explain variability in Y, and therefore maybe the regression coefficients don't make sense. So this kind of thing is very easy to see when there's only 2 variables because I can see the relationship between those 2 predictors. But what about our multivariate data set that has 14 predictors? Can you have strong relationships among those variables that we can't see in simple 2x2 plots? The answer is yes. So JMP has some graphical ways and numerical ways to detect correlation in your predictors. And the consequence of correlation in your predictors is inflated variance. both the prediction variance and the parameter estimate variance are inflated because, like I said, the variables are fighting with each other to explain variability and why. And that means the standard error gets inflated. And maybe when the standard error is inflated, then your signal to noise ratio, standard error is a noise, so the signal to noise ratio has a larger denominator than it should. And so the signal to noise ratio, in this case the t ratio, is smaller than it should be, and therefore the p-value is bigger than it should be, and you might miss real effects. You might miss real effects when you have correlation in your data. So I'll minimize this baby problem, and let's go back to our big data table with 14 predictors in it, and let's fit a model to these data. So again, I'll go to Analyze and Fit Model. Y is the Y, and I've got X1 through X14 in my model. Again, I'll just do minimal report and click Run. And so we've got a pretty decent R-squared, depending on your viewpoint. You might think that's fantastic or terrible, but 67% of the variability of my response is explained by this model. And 1 sigma of the unexplained variability is about 3. The signal to noise ratio is about 15, and that leads to a significant p-value. So this model is, again, useful in explaining variability and why. We should probably look at that residual plot. And I'm going to make it square. Looks beautiful, doesn't it? This is a great looking model. But is there any variance inflation that is happening because of those correlated predictors? And in fact, how much inflation is there? Well, there is a statistic that JMP calculates for you. You get one of these numbers for each term in your model, for each predictor in your model, and it's called the variance inflation factor. And you can ask for it by right-clicking on the parameter estimates table and telling JMP, hey, can I have a new column? And the column is called VIF, variance inflation factor. And here it is. High variance inflation means a high VIF. So high correlation or collinearity means that I have a high VIF. So you can sort this table by this column if you right-click and say sort by column, and we can sort by VIF and click OK. And now these big ones are at the top and the smaller ones are at the bottom. So what is this variance inflation factor? Well, it's related to an R-squared value. And it's a funny R-squared value. It's not this R-squared value of Y versus the predictors. It's related to how much variability in one predictor is explained by the other predictors. So it says, hey, because this variance inflation is high, that means that some other predictors are explaining variability in this predictor. Let's go look at that. I'm going to fit a model of X11, just the one with the highest VIF, versus the other X's, so X1 through X10 and X12 through X14. So my model has all of the predictors except X11, and I'm going to use X11 as my response. And if I click Run, I get, wow, look at that R-squared value. 98% of the variability in one of my predictor variables, X11, is explained by the other predictor variables. And so again, these predictor variables are fighting with X11 to explain variability over in this model in the response. So what is this VIF, variance inflation factor, and how is it calculated? You take this R-squared value, 0.98, and you take 1 minus that and then take the reciprocal. So the variance inflation factor is 1 over 1 minus R-squared, where that R-squared comes from regressing X sub 11, in this case, on all of the other predictor variables. So high VIF means worse correlation. So there's a lot of rules of thumb out there about how big of a variance inflation factor is too big. If you have an R-squared of 0.9, that corresponds to 1 over 1 minus 0.9 corresponds to a variance inflation factor of 10. If you have an R-squared value of 0.8, that corresponds to a variance inflation factor of 5. So Sometimes you'll hear about like 5 or 10 as a cutoff. Whatever you want to use is fine, but in the 60s, in the 17s, those are pretty big values for the variance inflation factor. VIF is a numeric way of detecting collinearity. There is a graphical way as well. And down here in this effect details report, there are these wonderful plots called leverage plots. Leverage plots have so much information in them. They can show significance, they can help detect outliers, they can help detect influential observations. And here we're only going to see how they can help detect collinearity. You get one leverage plot for each predictor that's in your model. The Y values on the plot are the residuals from regressing Y on all the predictors except, in this case, X1. So this is going to be Y versus X2 through X14. Find the residuals, save them, and you scale them back, you add the mean back in, and plot those on the Y-axis. And the limits here on the Y-axis are the same as the original data. And then the values on the X-axis, they're called X1 leverage. This is what you get when you regress X1 on all of the other predictors. Then you take those residuals, add the mean back in, and scale them so that they are, again, on the same scale as the original X1 data. And how do you detect collinearity is once you make the leverage plot, if you see that the points are shrunk in the X direction, so they don't fill up the entire X-axis, they only fill up this little bit of the X-axis, then X1 has collinearity with something else. And you can see X2 is even worse, isn't it? Well, we saw that correlation between those two variables earlier, so I'm not surprised that this is so bad looking. And if you scroll down, you can see that in every leverage plot, the points are shrunk to the middle. No leverage plot has the X values spread out all the way to the edges. So this is a graphical way to detect collinearity. And remember that you might not see this collinearity in the correlation matrix or the scatter plot matrix because these leverage plots understand more than just two variables at a time. Close this effect details here. Another graphical way of seeing the collinearity and detecting that there's a problem is in the prediction profiler. We've got a row for each response variable, a column for each predictor variable. It's the prediction profiler because at each of these settings, when I set my X's to each of these numbers, I predict from the model that I fit that I'm going to get a Y value here. The black line is a cross-section of this 14-dimensional plane that I'm fitting. So it is a line. The slope of X1 is positive. And in fact, the slope of X1, that is the slope of this line that's down here, a positive slope. The blue lines and the gray intervals that fill in those lines, or these curves, these are 95% confidence intervals on the predicted values. 95% confidence intervals on the predictions. And the telltale sign of collinearity is that the confidence intervals get super wide when you're on the edges. Super wide when you're on the edges. And why is that happening? Well, because of the correlation in the data do not fill 14 dimensions of space. They're correlated. They're in a cigar shape, a 14-dimensional cigar shape instead of a 14-dimensional spread out shape. The prediction profiler has this nifty feature called extrapolation control that you can turn on. And so you can see here now where the predictions actually make sense. Those lines have shrunk. And in fact, you can move these sliders around. You can shrink the areas even more. And so the areas where JMP is showing me the predictions, where it's showing me the model, are areas where I have data. And out here, I don't have data. And so with extrapolation control turned on, it's not showing me those regions. So that's pretty cool. There's also a warning feature. So now we have 3 ways of detecting collinearity problem. We've got variance inflation factor, we've got the beautiful leverage plots, and we have the prediction profiler. Now that we've seen that we've got this problem, how can we fix it? We said that X11 is fighting with the other variables. Well, should I just remove X11? We spent a lot of money to collect X11, and I'd hate to get rid of it. Can we still use X11's information? And the answer is yes. So I'm going to, again, minimize all these windows. I'm going to go back to that table with just 2 correlated predictors in it. And let's see some other things that we can do besides getting rid of one of the variables. So I'm going to look at this data set more, in more dimensions than just the scatterplot matrix let me do. I'm going to go to the graph menu and pull up a scatterplot 3D. I'll put all the variables in the Y role, and this gives me a 3-dimensional scatter plot of the data. And so I've got Y on the Y-axis, and let me spin it around to show you the graphs that we saw before. So we've seen this graph in Graph Builder. I've got Y on the Y-axis, X1 is on the horizontal axis, and X2 is going back into my monitor. And so you can see that positive relationship. And if I spin it this way, you can see the negative relationship between Y and X2. And if I spin it in different ways, like from this direction, you can see, well, there's that correlation between X1 and X2, right? And so you can see that the data are not filling up this 3-dimensional space. And in fact, they're not filling up the 2-dimensional space in the X1 and X2 plane. And really, I don't want to fit a plane to the data because I have just a line, right? I just have a line of data plus some random error. I don't really even have a plane. And so now I want to ask the question, can I, instead of fitting that plane, can I just fit a line to the data? And the answer is yes. There's really only 1 dimension of data, and the data follow a line pretty well. So maybe we can find this new line, right? This new variable, we can call this line a variable, and then use that variable as a predictor in the regression model. And that's called principal component regression.